The final bit of electric fields that I'm going to be covering in this short course is how charged particles interact with magnetic fields. So far we've seen how charged particles interact with electric fields in Millikan's oil drop experiment. Quick overview of some stuff that you might wanna know before we start this course. If we have two plates, a positive and a negative plate, and we have a charged particle, let's say it's a proton, right? A proton, when it has an initial velocity horizontal, it will tend to curve towards the negative electrode because it's positively charged, right? Oh, by the way, field lines, of course, go from positive to negative. Very important, you remember that. Oopsie daisy. Yep. Okay. And the positive particle will move towards the negative particle. And very similar to that, a negative particle will move in the opposite direction, right? Now, quickly before we move on to anything else, if we have a magnetic field between a north and a south, and we have an alpha particle or a positive particle, let's say a proton, is passing into this field, the way we work out which side the deflection is, whether it's out the page or how it works, is using Fleming's left-hand rule. And remember, Fleming's left-hand rule only works for positive particles. So in this case, if we use Fleming's left-hand rule, first finger in the direction of the magnetic field, second finger in the direction of motion of the alpha particle or the proton, and the thumb will point in the direction. So in this case, this proton will be deflected into the page. Okay? However, of course, if it's an electron, if it's a negative charge, it will be the same principle, but it will be deflected out the page, because it's an electron, it will be deflected in the opposite direction. Okay? So those are the main things that you need to know before we start this lesson. And in this lesson we're going to be seeing how charged particles interact in magnetic fields in slightly more depth. So, charged particles in magnetic fields. Okay. The reason why I want to cover this topic quickly is because of the fact that there are some applications for deflecting charged particles in magnetic fields, especially in cyclotrons, in synchrotrons, in basically particle detectors. There's a lot of magnetic field deflection that's required. And in essence, I need to first define to you guys how magnetic fields. So, for example, we know that if we have a north magnet's end here and a south magnet's end, a south magnet's end over on this side, we know that the field lines go from north to south, right? And we can see the direction of them moving using arrows, which makes sense. We can see it very clearly. But what happens if the field lines are going into the page or out of the page? The way we represent that is with X's and dots. Okay? An X, if you think of it as an arrowhead, an X is basically the fletched ends of an arrow. So if you see an X, the field lines are going into the paper, and if you see a dot, then they're coming out of the paper. So if we draw a quick membrane between the two magnetic ends, the X will be viewed when you're viewing the plane from this direction, since the fields are going away from this membrane, and the dots will be seen if you're viewing the membrane from this direction, because the field lines are coming into the membrane. So that's something you guys just need to know, and just grow accustomed to, because that's how convention defines the direction of a magnetic field into or out of a page. Right, okay. That's good. Now we know an electric field, or at least a magnetic field, is a field where a magnetic object experiences a force. But that's not particularly the case. charged particles can also feel a force in a magnetic field, depending on what angle they are incident to it. So I'm going to give us a quick example, okay? So using some other color, let's use a nicer color, orange. If we have magnetic field lines coming out of the screen, they're coming right at your face. What is this? One second, let me just clear up this mess that I've got on this side. Don't know what this is. Okay, that's good. So, one second. So back to this thing. If we have magnetic field lines coming out of the screen into your face, let's say, and we have a proton that's passing into a proton or an alpha particle, whatever. It's positively charged, and it's passing perpendicular. Okay, it has a velocity that's perpendicular to the magnetic field lines, or the flux lines. What you end up with, if you use Fleming's law, Fleming's left-hand rule, you find that the field lines are going into the page. My bad, because you can see the back end of an arrow. It's going into the page. And if you use Fleming's left-hand rule, you'll see that the particle or the alpha particle will be deflected upwards, right? It'll pass through the field and it'll cut it, and it will be deflected in such a way that in such a way that it resembles the arc of a circle. It will be deflected 90 degrees, basically. So, if charged particle cuts a flux field or a B field perpendicularly, then a force on that particle will be felt at 90 degrees to the direction of motion. So the force that's acting on this particle at any point will always be acting 90 degrees to the tangent. So if we draw a tangent to any point, the force will be acting perpendicular, like that. And if we draw another tangent over here, the force will be acting inwards, like this. So if you guys quickly pause the video and have a think about what sort of force this might be, it's always acting perpendicular to the motion. That should remind you of something. And if it doesn't, or it takes a bit more time, pause the video and think about it, and then come back. Alright, now that you've had to think about it, I'll tell you what it resembles. This sort of motion, right, resembles circular motion. But first of all, before I make the link to circular motion, I want to give you guys the equation that governs this sort of deflection. Okay? This equation, I'm going to make it nice and green. This equation is F is equal to B, which is the strength of the magnetic field, times the velocity of the particle in the magnetic field, times by Q, which is the charge of the particle. Okay? This is a very important equation. Learn it. So, let me quickly put a box around it. Okay, F equals BVQ. Okay? And that governs the force, the perpendicular force that's acting towards the motion of the particle. Now, I mentioned very recently that it's similar to the circular force, or centripetal force. And centripetal force is defined by F is equal to mv squared over r, right? These two forces basically are describing the same thing. So, in essence, they're going to be equal, and we can equate them. mv squared over r is equal to B, V, Q. Of course, we can now rearrange this, so the V's will cancel, and you can rearrange it for R. And what you'll end up with is an equation, a very important equation. MV over BQ is equal to R. Okay? The radius of the deflection is equal to this quantity. Now, the radius of deflection is actually important in identifying particles. So, particles of different masses, of different velocities, will be deflected at different radii. The radii will increase as the mass increases, as the velocity increases, the radii will increase. In cyclotrons, etc., if you are increasing the velocity of a particle, if you're trying to speed a particle up, the radius will increase. So to make sure that the radius stays constant and that the particle stays moving in a circular direction, you have to keep the radius constant. You'll have to increase the magnetic field strength as well, because the particle's charge will stay constant, right? So that's just some stuff which we'll review this when we're talking about cyclotrons. But this is an important association to make, that the perpendicular force that's acting in a magnetic field for a charged particle is analogous with the circular motion for the centripetal force that, for example, a gravitationally bound object might feel. In fact, we can take this one step further, and this equation, we can actually relate this to stuff that we reviewed a long time ago in one of my previous videos. So, you guys might remember from the previous videos me describing how a wire is deflected. So we have a north magnet, we have a south magnet, and we have a wire running through with a current in that direction. We know that the wire, by using Fleming's left-hand rule, will be deflected downwards, right? It will be deflected downwards. And we basically had an equation that governed this, which is F is equal to Bill. To be honest, we can actually break that down and work it from first principles. What is current? Current is the movement of electrons, or the movement of charge, from this area to that area, right? It's the movement of charge. And that movement of charge creates that a deflection in that downward direction. It's not the movement of, I'm not technically correct in saying that, because electrons move in the opposite direction, but let's just assume that we're talking about positive charge moving in the direction of the current. Okay? That positive charge is basically this quantity over here. It's a positive charge that's moving in a perpendicular magnetic field, a magnetic field that's perpendicular, uniform magnetic field that's perpendicular to its direction of motion, which induces a centripetal force, which is this force that we're experiencing downwards, right? So, in order to get F is equal to BL as an equation, what we can do is we can take F is equal to BVQ, right? What is velocity? The speed at which this charge is moving at is distance over time. So B times distance, or in other words we can say it's length from this part to this part where the uniform magnetic field exists. That's, let's say it's the length, okay? Divided by the time, distance over time, times by Q. Well, what is Q over time anyway? Charge over time. Charge over time is just current, right? Hence, what we get is F is equal to magnetic field strength times current times the length. F is equal to Bill. So you can see how these two equations are now linked, right? Similar to that, if we, for example, if I gave you another example of, we have another magnetic field here. Let me use a lighter color. We have another magnetic field with field lines going into the screen. And let's say we had a wire that's passed through the magnetic field. we're having a wire, right? A wire is being passed through this magnetic field over a distance of, let's say, x, from here to here. It's being moved from here to here over a distance of x, right? And of course it's of length L. From first principles, if we assume that there's one electron or one charge per unit of that per length of that wire that we're using, we can then determine the induced EMF that's the EMF. There's going to be an EMF that's induced in this length of wire if we don't connect it to a circuit, right? And if it's not, if it doesn't have any of its any circuit of its own, instead of force in this instance, we'll be generating EMF, but it's a very similar idea, which is why I wanted to bring it up. If you guys remember from previous equations, phi is equal to BA, right? Well, the magnetic field strength is going to stay constant per area, but the area that's going to be traveled by this particular piece of wire is going to be Lx, right? Therefore, we can work out what phi is going to be. Phi is basically going to be BLx. Phi is going to be BLx for this wire, and based on that rate of change, or the rate at which it's moving, if that's divided by time, right, over the time period that it takes for this movement to occur, we can then work out that phi is equal to BLV. And this is an important equation that you might want to remember as well. The reason why I'm pointing this out now is because I want you guys to be able to combine equations and relate equations. So this equation can form this equation, and it's important to realize that there are these links in physics that you should be able to rely on, or work out from first principles if you can't remember them in an exam, or if you ever have to use them in day-to-day lives. It's important to be able to work them out from first principles. So I think that's about it for electric fields that I need to teach you and how they function. I'll be doing one more bit on the application of electric fields and deflection of particles in cyclotrons and synchrotrons, but that's for another day. So I'll catch you guys in the near future. Take care, and subscribe to SciSync if you have time. I'll be posting lots of videos, not only on physics, but also on chemistry, on biology, all different types of topics. So please stay tuned, please subscribe, please like the video as well, and I'll see you guys in the future. Bye bye.